Hello everyone. Welcome to the INQA seminar series. Today with us we have Nicolo Defenu, and he's gonna talk to us about some new insights in the Kibble-Zurek mechanisms. Go ahead.
Well, thank you very much for your kind introduction, and thank you everyone for being here. So I'm gonna be brief. I think the topic of the seminar is quite interesting, but also quite light. So it's adapted for the late time of the day we are, at least in my time zone. So the topic, so what I'm gonna show you is basically some advancement that we had made in the description of defect formation in a many-body quantum system with long-range interactions, and I'm also going to do a comparison to what happens for system with nearest neighbor interaction. So first of all, let me give you a brief introduction to what I mean when I talk about system with long-range interactions. So systems in long-range interactions are quite in the center of some interest today due to the fact that they can be realized across different experimental platforms. And basically, we call a system long-range interacting when its microscopic components interact via a two-body potential, which the case as a power law of the distance between those components. So any kind of interaction r to the minus alpha with alpha some real number larger than 0, we call it a long-range interacting system. And as I say, these kind of interactions are quite common nowadays because they can be realized across different quantum simulators. For example, there is the case of cold atoms into cavities where we confine a quantum gas within an optical resonator. And this, when you pump the optical cavity with a laser field transversally to the cavity direction, what happens is that the light is scattered by the atoms and it's in the transverse direction within the cavity. And depending on the intensity of the pump of the laser and its frequency, one can reach a situation in which there is light in the cavity, there is a finite light intensity in the cavity, and so the atoms feel a long-range interaction, which is flat because it's mediated by the cavity photons, which are basically a wave function in the cavity that does not decay. Similar situation arises in trapped ions quantum simulator, where you have trapped ions that are arranged into crystals, and the interactions are mediated by the phonon of the crystal, but by sending microwave fields at a certain, with a tunable angle across the crystal, one can modify the dispersion relation of the phonons so that the interactions mediated by the phonons are also long range and decay as a power law, and the power law is tunable because it depends on the shape of the dispersion relation of the phonons, and one can tune basically interaction that range from 0 to 3. Sorry, this A here is alpha, there is a mismatch in notation. Also recent experiment in Rydberg gases, which are becoming quite popular as a quantum computing and quantum simulator, display long-range interactions. In most of the long-range interactions which appear in this simulator, in these quantum simulators, are not tunable, and they decay of 1 over r to the cube or 1 over r to the 6, depending on the orientation of the dipoles of the Rydberg state. But their intensity is very strong, and depending on the experimental situation, they can be also used to mimic like cluster interaction, so flat cluster interaction. So these are basically these are just a few of the various platforms which can simulate long-range interactions. Longer discussion about how these long-range interactions are realized and which kind of interesting physics can be realized within them can be found in this review article, which I have recently co-authored with some of my collaborators, Tommaso Macri, Guido Pagano, Tobias Donner, Stefano Ruffo, and Andrea Trombettoni. And there is also some insight you can be interested in. It can be found in our review article that's just on the archive with Alessio De Rosa and Silvia Pappalari. Okay. After having referred to my recent literature, I wanted to thank the collaborators of the research that I'm going to show you, which are Giovanna Morigi, Tilman Hens, and Michael Kastner for the first part of the talk, and Lorenzo Buffoni and Stefano Tergiardini in the second part of the talk. And also I would like to acknowledge the funding agencies that are the Swiss National Science Foundation and the ERC starting grant Quantum Long Range Networks that are supporting my research in this and also in other interesting aspects of long range interacting systems. Okay, now it's time to delve into the topic of my talk. And so, as I said, as is explicited in the title, I am gonna. Oh, I cannot go back for some reason. Okay, just a moment. Sorry. So, as I said in the title, basically, my interest is to build a effective theory for long-range interactions. I don't know why the cursor doesn't work. Maybe it's better to do it in this way. So what I'm interested in is to build an effective theory, so a theory that describes the defect formation in a many-body quantum system at low energy. So that's basically able to describe what happens to systems that are in the thermodynamic limit, where we know that it's the low energy states that are important. But in order to do that, and in order to be concrete, I like to introduce my theory into a concrete example. And this concrete example is the Ising model. So the Ising model is a model of interacting spins. So you see these are quantum spins, so these are Pauli matrices. And the first term represents a ferromagnetic interaction. And as you see, the only addition that I do with respect to the standard case that you find in textbook is that my ferromagnetic interactions are basically within all spins. So this sum does not extend only between nearest neighbor, but it extends over all sides of a one-dimensional lattice. Let's focus just on the one-dimensional case. And with the intensity Jj that I will discuss in the following. Also, the system has a paramagnetic transverse field, which is H, and as you all know from textbook, when the ferromagnetic interaction is much larger than the transverse field, one finds that the system has two ground states and there is spontaneous magnetization in the system. Of course, this happens in the thermodynamic limit. And for J, that's much smaller than the transverse field, one is in a paramagnetic state where the correlation functions are exponential. These two phases in the thermodynamic limit are separated by a second order phase transition, which occurs at a quantum critical point, which is at a finite value of the external transverse field. So all of this is exactly as it happens in the standard nearest neighbor quantum Ising chain. The only addition that I made is that my ferromagnetic interactions are now power law decaying. You see, they are power law decaying. And as a function of the power alpha, there are different interesting regimes. There is when alpha is larger than 1, which is the dimension of the system, these interactions basically modify the low energy spectrum of the quantum phase transition, but they leave the thermodynamic properties mostly unaltered. While for alpha smaller than 1, these interactions become basically non-extensive because the scaling of the ferromagnetic energy for a ferromagnetic ground state is more than linear with the system size. And so we need to include a scaling factor n to the alpha, and this scaling factor is reported like in here, and this scaling factor makes in such a way that the ferromagnetic contribution to the system internal energy and the paramagnetic contribution have the same extensive scaling. Nonetheless, this kind of procedure maintains the key ingredient of strong long-range interacting system, which is of the system is non-additive. So you cannot separate the system. You cannot say that separating the system into the sum of the energy of two subsystems is the same as the energy of the total system in the thermodynamic limit. And the reason is that the contribution from boundary terms in the thermodynamic limit for strong long-range interactions is not negligible. And as we will say, this is quite important for what follows. Okay, so basically now let me show you what's the dynamic that I have in mind. So in this seminar, people often have talked of quantum annealing. This is also a case somehow of quantum annealing from a more theoretical perspective. So what's my interest is in the interest of, and I'm showing this example in the case of the nearest neighbor case, so alpha equal to infinity, but it will be valid for any alpha. So basically what you see, so the idea of the dynamics that I have in mind is to take the transverse field and to make it time dependent. And to make it time dependent in such a way that we are crossing the quantum phase transition. So the control parameter lambda will become a linear function of time. The control parameter is just the values of the transverse field minus the critical field. It becomes linear in time with a velocity, which delta is called the ramp velocity. So you see there is a ramp across the quantum critical point, and the ramp velocity is delta. And by procedure, I call it an annealing procedure because it's in the limit in which delta goes to 0. So I want to do the slow limit in such a way that I am at each time close to the instantaneous ground state. And I'm going to focus on two. So basically, my dynamics is always going to start with initial values of time that's order of -1 over delta. So it means that basically the idea is that the control parameter is far into the ferromagnetic phase, and then it crosses the critical point and it goes into the paramagnetic phase when the time reaches its final value TF that can, and I will discuss what happens as a function of TF basically. Okay, so what happens when you do this procedure into the Ising model? So what happens is that there is an adiabatic condition, and the adiabatic condition is reported in here. So where delta is the instantaneous gap of the system. So imagine that you have this system and the system is at equilibrium. At equilibrium, you can find the gap between the ground state and the first excited state. Now, for each value of h, which is far from the critical point, the gap has a finite value. Now, you collect the value of this equilibrium gap as a function of time, treating each of the instantaneous Hamiltonian at time t as equilibrium Hamiltonian. So this adiabatic condition only involves equilibrium quantities, so quantities that are calculated at equilibrium, but basically that are only time dependent due to the fact that the Hamiltonian is changing in time. But you are not really solving the time dependent Schrödinger equation. You're just solving each instantaneous Hamiltonian. You're solving at equilibrium, and you have a curve which gives you the equilibrium gap, the instantaneous gap, as a function of time. Now, the adiabatic condition for this system is when the derivative of this instantaneous gap, as long as the derivative of this instantaneous gap is much smaller than the gap to the square, then the system is adiabatic. Okay, and this is kind of intuitive in my opinion. So it means that as long as the spectrum of the system is not varying so strongly with respect to the value, to the minimal gap itself, it means that the system is able to follow the drive, and it means that the system started in a ground state, it remains in the ground state, but for very weak corrections, which we call the defects. But what happens when you cross the critical point? Well, when you go close to the critical point, there is situation, so you know that the gap is closing at the critical point. And since this has to be a positive quantity, so basically there has to be a moment in which this adiabatic condition is violated, and we call this the freezing time. So as you progress with time, the adiabatic condition becomes worse and worse obeyed, and as you approach the critical point where the gap is closing, you have a freezing time at which this equivalence doesn't hold anymore, and the system enters in the so-called impulse regime, where the system is basically frozen. It cannot follow the drive anymore. The Hamiltonian is changing, but the ground state is frozen, and so the system wakes up at the freezing time of the opposite sides of the ramp that we should call at the freezing time, but we call it freezing time because for symmetric gap, the modulus is the same. At the freezing time, the system wakes up with a ground state, which is not the ground state of that instantaneous Hamiltonian, and it contains defects. One has a very nice geometrical interpretation for these defects as long as the system is in the nearest neighbor case. So for alpha equal to infinity, where my Jij is basically very short range, nearest neighbor, but even values of alpha which are finite but where they are large, they will show a situation like the one that's reported into this picture. No, you will have domains of ferromagnetic domains which were trying to melt, but they didn't melt completely because they were kind of frozen to the correlation length that they have at the freezing time. And so you can also, corresponding to the freezing time, you can define a corresponding freezing, so like freezing size, freezing length, which tells you the length of the defects, the length of the domains, and so basically that tells you how many defects, the density of defects that you have, which are the ones that arise at the border within the domains. And I am sorry if I made the plot in 2 dimensions, even if this is a 1-dimensional case, but I think that the 2-dimensional plot makes it's more interesting. So, okay, as whatever I told you up to now, it's kind of very well known, and it has been studied along is the Kibble-Zurek mechanism as it working nearest neighbor system. And for the case of the quantum Ising model, this has been studied in several references. I'm reporting here only the one that I think were the first. So they were basing some of, so I think the most important, but like the most, the one that summarized better the field are this one from Dorner is the first author, in which for the first time it was computing the density of defects of the quantumizing chain in 1 dimension with nearest neighbor interaction, and they were using a finite size scaling argument to relate basically the density of defects with the critical exponents at equilibrium. There is another paper by Polkovnikov which basically does the same calculation more in general, so for generic system, and it uses a adiabatic perturbation theory argument and gives you an exponent theta, which reads in this way. So basically the exponent theta describes the density of defects, but if you wish it also describes, maybe it's better to use to define it in this way. It describes the excess energy generated by the annealing dynamic. So you ramp the system through a critical point, and when you go at very large times, here I write time to infinity, but what's actually important is just that the time is much larger than the time at which the system was at the critical point. So for any ramp that goes across the critical point and goes far from it, so start far from it and ends far from it, you can define an excess energy, which is basically the energy of the defects, so the energy, the displacement from the exact ground state, which is caused by the presence of defects in the state. And this excess energy receives its most important contribution from the scaling close to the critical point, and so it has a critical scaling that's described by delta to some exponent theta. And this exponent theta can be related to the equilibrium critical exponent exactly in the way that I described you before. So due to the fact that the length of the defect is basically the one of the freezing length. So as I say, there were 2 arguments, one for the finite chain, one from adiabatic perturbation theory. And then a bit after, so I think 1 year after those arguments came out, there was also an exact solution given by Jarmaga of the quantumizing chain problem with nearest neighbor interaction. And as you see, all of the results for this critical exponent, for this dynamical critical exponent theta were different. But what turns out that for the Ising model, all of these descriptions are equivalent, because if you put z nu equal to 1, you will see that all of, so basically all of these results give you 1 alpha. So because for the Ising critical exponent, Z nu is equal to 1, but also Z and nu are both equal to 1 singly. And so you see that basically these results all agree. Sometime later, so much more recently, in 2020, Del Campo and collaborators, so they've made some nice study, and they showed that one can also find universality not only in the excess energy, not only the density of defects, but also in the probability with which the defect is generated. So the entire probability distribution for the number of defects has some universal behavior. And so they studied the system of sides L. So again, since these are universality arguments, they can apply both to the two-dimensional classical system and to the one-dimensional quantum case, because the two systems are in the same universality class. They can be mapped into each other. And they studied the case of basically the two-dimensional classical system. As I said, the universality is exactly the same. And they showed that the probability to generate n defects is a binomial distribution that depends on these effective sides of the system and by a parameter p, which is a fixed number which depends on the system in discussion. And when you put together this information, you have that the probability to generate a certain number of defects n into the system depends, of course, on delta through n and also through p. And you can show basically that you have the results. It's a binomial distribution that becomes basically sharper and sharper as you send delta to 0, as you expect, because as you send delta to 0, the number of defects have to vanish, and this binomial distribution becomes more and more skewed towards the 0. Okay, so this was a very nice, interesting result. And now I will show you what we found for the long-range interacting case. So first of all, it's important to understand that we are talking of a system in which long-range interactions are smaller than the dimension d. And in specifically, I'm going to talk a lot about the case in which alpha is equal to 0. So basically, there is no decay of the interactions. They're flat interactions. And obviously, if you do, as I said before, the systems are non-additive. So if the interactions are flat, there is no hierarchy between surface and volume. So a surface effect has the same order as a volume effect. But even more, and this leads to the fact that the argument of having topological defects in which you have basically large magnetized domains that are connected to smaller domains of the opposite magnetization with a defect arising at the edge, this kind of argument does not work. You cannot use freezing length arguments, sides of the domain argument, in a long-range interacting system, because in a long-range interacting system, there is no spatial resolution. There is no boundary effect. Everything is a bulk effect. So how do you describe the system of when it has flat interactions? Okay, so first of all, let me say a few words. Why is this problem interesting? So the problem started to be interesting for us because we noticed that if you take the arguments of the previous paper that I've shown you, that they all agree for the Ising model, if you take the case of a fully connected Ising Hamiltonian, so this is exactly the same Hamiltonian as I said before, but with alpha equal to 0. So all spin talk to any other with the same ferromagnetic interaction strength. So this system can be recast in the form of a single giant spin, which is the combination of all the single side spins, which has a self-interaction term as x to the square, basically. Now, this system is very well known and studied, and we know that it has a quantum phase transition at a certain value of h, and this quantum phase transition is of the mean field type. Since the quantum phase transition of these models of the mean field type is the value of the correlation of the critical exponent z nu, so the multiplication of the dynamical critical exponent z and the correlation length exponent nu, is not 1 as in the Ising model, but it's in 1/2. And when you take the the results for the three papers that I've told you before, the finite size scaling argument and so basically the finite size scaling argument and the perturbation theory argument from Polkovnikov, when you take these two results and you plug the critical exponent of the fully connected model, the two results do not agree. So one gives you 3/2 for theta and one gives you 1/3. So you see the two results do not agree with each other. So this is what first moved our interest. So what we did is we take our giant spin, we take our, giant spin self-interacting, which is the Lipkin-Meshkov-Glick, and we bosonize it through an Olsen-Primakov transformation. This Olsen-Primakov transformation is, of course, an approximation, but it's a very good representation of what happens to the system at low energy. And so we believe it's the exact description for the critical dynamics close to the quantum phase transition. When you do this procedure, so when we apply the Olsen-Primakov transformation, you basically substitute the spin operator with bosonic operator as given in this table above, what you obtain is basically a single boson Hamiltonian for the Lipkin-Meshkov-Glick. So when you apply the Olsen-Primakov transformation, what you find is that your Hamiltonian looks like the one of a single boson with a certain energy delta, which is exactly equal to the gap of the system. And the cool thing of single boson Hamiltonian is that we can solve it exactly. We can give you the wave function, and we can solve the dynamics exactly at each time. And so we can compare the adiabatic dynamics, the one that will be obtained if the system were always satisfying the adiabatic condition, with the exact dynamics, which is the one that that's really occurring close to the critical point. We find three regimes. First of all, we find that the results of the system do not depend independently on the size and on the ramp velocity, but all of the physics of the system at low energy is encoded by a collective variable n multiplied by delta. So size of the system multiplied by ramp velocity. So this already tells you that this kind of system has a universal scaling in the dynamics. This is a bit different from the one that you expect from the short range, because you have this collective variable n to the delta, and as I will show you, basically this system is much more non-adiabatic than its nearest neighbor brother. So indeed, what is this result telling you? As long as n is, so as long as the system size is comparable in with 1 over the ramp velocity, so these are dimensionless units, as long as these two numbers are comparable, the system is in the adiabatic regime. It satisfies the adiabatic condition at all time. Why? Because if the system is finite, there is no perfect quantum critical point. The quantum critical point has a finite gap, and the finite gap is large enough when this condition is met to leave the system always adiabatically. And so this means that basically the residual energy scales analytically with delta to the square. If we take instead the case in which the system is in the thermodynamic limit, so the thermodynamic limit is taken first, and then we take the slow drive limit, so delta gets smaller after the thermodynamic limit, but we focus on the case in which the quench is critical, meaning that the final time is exactly 0, so I stop my ramp exactly at the critical point. There I find something that's reminiscent of the Kibble-Zurek mechanism. So there I find that my Q scales with an exponent delta to the theta, and I will show you what's theta later, but there I find an actual Kibble-Zurek scaling. But when I do the full ramp, so when I ramp across my critical point and I take a final time, which is of the same order of the initial time, which is of order 1 over delta, and I also take my thermodynamic limit first, when I find these two conditions together, which is the case which was giving a Kibble-Zurek scaling for the short-range model, here I don't find any scaling. Here I find that the excess energy Q is of order 1. So the system is strongly non-adiabatic because it generates an amount of defects which is independent of delta and which survives even in the limit delta going to 0. So even when delta goes to 0 and the ramp is adiabatically slow, this is a quasi-static transformation, this system fails to be adiabatic and it generates a finite number of defects. Okay, we did some numerical calculation to show this, and so you see that here as a function of delta. So if you do a critical quench as a function of delta, basically you can find the different regimes, so these curves are different values of n. And what's important is that you witness here that if you take a delta 1 to the third, which will be the prediction from the adiabatic perturbation theory result, you find that when the thermodynamic limit is taken 4, so this curve is for n very large, you see that the two things agree quite nicely. On the other hand, if you do the calculation with the final time TF at plus infinity, so far away from the critical point, you find, as I told you, that the result is universal as a function of lambda, so it depends only on the combination size of the system multiplied by delta. And quite remarkably, the results from our effective theory, so you see these curves are the results from our effective theory, so these are the single boson Hamiltonian with time-dependent gap, agree quite nicely with the picture that's obtained for the exact numerical solution of the Lipkin-Meshko-Glick model. So these are the data from the exact numerical solution of the fully connected Ising model, which have been obtained by Acevedo et al. In this physical review letter. And if you look at the shape of the curves, they perfectly agree. Obviously, there is some mismatch between the values of the energy, but this is due to the mean field energy. This has nothing to do with the physics of the system. The universal physics is quite nicely reconstructed. Interestingly, our effective theory is so powerful and yet simple enough that we can also give you the full distribution of the defects. Obviously, these defects are not topological defects, but are somehow, because there is no topology in the system is a fully connected one, but still I can define a number of defects by the occupation number of the boson. So how many, so if there are no boson, the system is in the ground state. If there is one boson, I have one excitation. So I can characterize the number of defects by the excitation, the state of the single boson. And when I do that, so when I decompose my time-dependent state into these states, in these bosonic states, what I find is that the distribution of defects for this Hamiltonian is very far from being binomial. So the binomial distribution that was found in the Riener's neighbor case was applying both to the classical and to the quantum case. But in the case of long-range interactions, the distribution of the defects is, it doesn't have any classical counterpart, no? Binomial distribution is a distribution that you can also obtain by turning a coin. You have it for the defects in the quantum system, but it's the process in which that generates this defect is somehow classical. While here we find a distribution of the defects that non-classical, in the sense this is a negative binomial distribution for the long-range model, and negative binomial distribution cannot be obtained in any classical extraction process. Somehow they are special mathematical objects which arise here due to the intrinsic quantum nature of this system. Okay, there is somehow the results are very different from the one of the nearest neighbor case, but still you see the same physics, no, for the number of defects. So it's more probable to generate a low number of defects, and as you increase with the number of defects, the probability is smaller. Here we did the calculation even for a much more general drive, so not just for the linear case that I show you in the nearest neighbor system, but please just focus on the case in which eta is equal to 1. So the blue lines, it's more interesting, and there is no reason to look at all the other different eta, which are interesting but not crucial to this talk. Okay, so basically this is the final result for what I wanted to tell you. So quantum system with near stable interaction, the universal low energy dynamics is the same as in the classical case. As a result, the probability to generate defects is basically follows a binomial distribution, while for the fully connected long-range interactions, the process, the quantum dynamics is somehow stronger. Somehow the quantum features are enhanced by the long-range interactions. And for this reason, you first find that the system is really non-adiabatic. So in the Kibble-Zurek mechanism, the density of defects still goes to zero when delta goes to zero, even if it does that in a non-analytic fashion. But in the long-range case, there is no Kibble-Zurek mechanism. When delta goes to zero, the defects remains of order one. And also their distribution is a negative binomial, which cannot be obtained in any classical extraction process. And somehow this is due to the intrinsic quantum nature of the system. Okay, this is all what I wanted to tell you. I thank you for your attention, and I hope you have questions on this.
It's for a nice talk.
Thank you.
If while people are thinking about questions, I can ask a quick one. So you said that you will tell us what the theta is, but did you actually tell us what the theta is in your own results?
Yes. So in our own, so basically for the quench across the critical point, theta is somehow zero. No, as I say, there is no real Kibble-Zurek mechanism. But if you do the quench exactly at criticality, you still see a reminiscence of the Kibble-Zurek mechanism, and this is with the exponent 1/3. So if you do a quench exactly at the critical point, you find somehow the exponent that was predicted in this physical review letter. But the interesting part is that this formula for the nearest neighbor case, it applies both for quenches at the critical point and quenches across the critical point. While in the case of long-range interactions, the formula only applies to critical quenches, and when you go for quenches across critical points, this formula doesn't hold anymore, and you find this order one number of defects.
Suppose there's a question in the chat. I can read it if
Thank
that's
you, because
okay,
I
or
cannot
you can
find.
just say
Yes.
I can ask. So as you said, if you quench at the critical point, you see this Z nu over 1 plus nu Z formula. But I'm used to post-critical dynamics in higher dimensional models, lattice models and so forth, being associated with coarsening. So how does your result relate to this? Can it be interpreted as a coarsening?
But you see, basically, it's very, as I said before. So basically, it's quite difficult because coarsening is somehow this picture. Even if I understand, maybe it's not so nice, but it's somehow intended to represent coarsening. No, you find this region that shrinks, but in a fully connected model, there is no reason. So there is no notion of distance.
Yeah.
And if there is no notion of distance, there is no. How can you describe coarsening? So you can flip a spin. There is no reason for flipping spins that are close to each other's.
Sure. If you have but like there are some alpha which are qualitatively matched to different models of different dimensionality. So is there no notion?
So basically,
no notion of distance there.
So basically, okay, what I was describing here, as I said, is specifically working very well for alpha equal to 0.
Yeah.
Okay. And so there is really no notion of dimensionality. My expectation, which is a quite strong expectation, I have to say, is that it will work for all cases which alpha is smaller than the dimension. And we know that when alpha is smaller than the dimension, basically, we cannot find a good definition of correlation length. And whenever you don't have a good definition of correlation length, I think you cannot have a good definition of coarsening. So you cannot describe the physics in terms of coarsening, because you don't have somehow this idea of domains interacting with each other at the boundary. So I would say that coarsening still stops applying for each alpha that's smaller than the dimension of the system. But as I said, my results specifically are derived for alpha equal to 0. So the fact that I believe that they apply to each alpha between 0 and 1 in one dimension is a conjecture, but it's a somehow strong conjecture.
Thanks, great answer. Yeah.
Okay, I can ask another question, which is that so you look at the total energy of all the defects, not the density of the defects, right? And so you have those two scalings. One scales with delta and another doesn't. So just a simple question: which one is lower, right? So if it's delta to some power or of one, then which one is smaller in this particular
No,
limit?
basically this. So order one means that theta is 0. So this is all basically this, the one on the right. So this one always wins over this. So this is always larger. But this is a kind of, so any finite theta will tell you that the number of defects goes to 0 when delta goes to 0. No, any theta larger than 0 tells you that, so theta has to be larger than 0, because it's basically when you send the ramp velocity to 0, the transformation becomes a quasi-static one, no? Like the one in a Carnot cycle, like the one, so like the quasi-static transformation that we're taught in thermodynamics. They are infinitely slow. And if it's infinitely slow, you expect the system to always remain adiabatic. And for a system, even for critical system like the one of the Kibble-Zurek mechanism, this is true, because when you send delta to 0, the number of defects goes to 0, even if it does that a bit slowly. So it does it with a theta that is normally smaller than 2, or sometimes even smaller than 1. And so the number of defects goes to 0 very slowly. But this system the long-range system is special because in this system it's of order 1, meaning that even when delta goes to 0, the number of defects remains finite. The number of defects is somehow cannot be sent to 0 by making a quasi-static transformation. And this is due to the fact that the thermodynamic limit and the quasi-static limit, so the limit n equal to infinity and the limit delta to 0, do not commute for this long-range system.
See. Well, if there are no other questions, I will ask one more, which I don't think, yeah, essentially, if you can comment on this. So you said something about the distribution that is hard to make classically. I mean, under my impression, if it's just a distribution of a finite number of possible outcomes, then you can make any distribution classically as long as you have a table of it, pretty much table of probabilities of these outcomes. You just need to flip a lot of coins, essentially, and then you need to process those coins in summary.
I think negative binomials cannot be obtained by any coin tossing. So this is the negative binomial, so meaning that the distribution that I'm talking cannot be obtained by any coin tossing. This is what I understood by the mathematics.
I'm not entirely sure what is this mathematical result that you're referring to, because naively, right, for every distribution you have the distribution function, right? So it's some kind of function that takes in a random value from from 0 to 1, and depending on its value, it gives you one of your possible outcomes. So, and if the distribution from 0 to 1 is uniform, then essentially using that value from 0 to 1 to kind of evaluating this distribution function gives you one of the outcomes, pretty much, right? So that's how you generate any distribution of any random variables with like a finite number of outcomes. So, and clearly you can generate a uniform distribution of a real number from 0 to 1.
Okay, so basically, I'm not sure I am. So what I can tell you is this. So the negative binomial distribution is understood like this. So you take a total number of trials. So you specify the number of successes and the number of failures. And then what you have to do, so basically, so you can have this generalized binomial by asking, if I do n trials, what's the probability of having r successes? Okay, and you obtain this generalized binomial distributions. So the binomial distribution tells you what's the probability to have one success after thought failures, and this gives you what's the probability of having r successes into given k failures. So these are the generalized binomial distributions. But the negative binomials are obtained when you take the number of successes to be a fractional number. And this, I think, it cannot be. So when you take this to be a fractional number, I don't know if you can simulate it by making more extraction properties, but I think no.
Well,
But
yeah,
this,
clearly a fractional number, you can't apply the same operational definition anymore, but
I don't
it's
know
still
if
a
you can.
distribution. So
It's still
you
still a distribution, of course.
yeah, you can definitely approximate it to arbitrary precision by just using
No, this,
solution from the fragments.
of course, I didn't want to say, that this you cannot, of course, this is a classical, this is a function. So this is
Yeah,
just a function. I'm just
yeah.
saying that the process that generates these defects is not classical. So
Okay, I understand now.
in the nearest neighbor case, the process is a classical process. Is if you read this nice physics article, it explains you how can you match this defect formation with a coin tossing. So it's a classical process. You say, okay, what's the probability to having a defect there? Okay, it's like tossing a coin. What I'm saying here in the long-range system is not like tossing a coin. It's like tossing 1/2 of a coin. So it's something that it's not a classical process. Of course, the function is a classical function, so you can sample it with a computer to arbitrary precision. It's a classical function. It's just it's a classic. There is no. It's a function, so you can you don't. It's not anything different than a function. I'm saying just that the process is not a classical process. You cannot map it to a coin tossing. It's not a coin tossing. Or if you want,
Good,
it's
thanks. I think I
right.
understand
Very
now.
good.
Is
Thank you.
is there any other questions?
See
Oh, there
something in
is
the
one.
chat.
You can read it.
Myself again, Jack.
Mhm.
Actually, I work just for context. I work for D-Wave. I'm a statistical physicist. You've spoken about an ordered model here. So, what are the consequences for disordered models? Either disordered by sparse, long-range sparse, long-range random J ferromagnetic, or even random frustrated.
So basically, this is a low energy theory. So what's really important in here? So basically, you can easily generalize to all the cases you have said. It all depends on the spectrum of the low energy spectrum. Okay, so the reason why this low energy theory works differently than the nearest neighbor case is that the spectrum is gapped. Okay, so this is very different from, so in a system which has local interactions where you can define the notion of correlation length. If you go into the thermodynamic limit, the spectrum becomes continuous. No, so you have a continuous spectrum. But for the system that has strong long range interacting, and specifically for this alpha equal to 0 case, you can map the many body system into a system that's basically a local, which is a system which is really basically a point. No, you see, I map the many body system into a system which is a single site. And since this is a single site quantum system, its spectrum kind of remains discrete in the thermodynamic limit. You still have a gap, a finite gap, even in the thermodynamic limit. And this is due to this gap nature of the single, I'm talking about the single particle spectrum, so the spin wave spectrum, if you wish, due to the fact that the single particle spectrum is discrete. When I use the effective theory gives me the result that's not Kibble-Zurek. Because instead of having a bunch of continuous defects that I have to integrate over, I have just one single defect with finite gap, and so I get this result. And this result, as I said, even if it's a low energy theory, it agrees very, very well with the numerics. So to answer to your question, if you take a system which has frustration and everything, might be long range frustrated, what normally happens is that in a pure long range system, the spectrum is completely discrete. In a purely local system, the spectrum is the single particle spectrum is normally continuous. If you go to a system which has long range frustrated interaction, you have an interplay of discrete spectrum plus some continuous region, And it depends if the spectrum at low energy is still discrete. I think it will be our results that applies. If instead the frustration is strong enough to make the low energy spectrum continuous, to split the degeneracy and make the low energy spectrum continuous, then you will have a result of the Kibble-Zurek type. I hope that this was understandable.
Yeah, I have to go and read a bit more on the theory, but yeah, thank you.
Very well. If there are no further questions, thanks everyone for coming, and it was a great talk. See you all next week.
Thank you very